You are welcome for this lesson. In our lesson today, our major focus is going to be at looking at calculations involving specific heat capacity and specific latent heat. So those are the calculations we are going to be looking at. But as we go into our calculations, I want to remind you about some of these constants that we shall be applying whenever we are dealing with some of these calculations. So always look at the question paper, always at the front of the question paper, they are always given, or at times they can be given together with the number or with the item. But as we go into this, there are some things you need to know. Calculations involving specific capacity, involving latent heat can be well done using what you call the heating and what you call the cooling curves. So we have what you call a heating curve, and it will look like this, whereby that curve, we have it where we have the temperature, against what we have as our time. Now, these curves show us how the substances change state from one state to another. So when I have, this is going to be my curve, I want to show you what you need to know going forward. Now, this is where I have my 0. So whenever we have any substance that is below 0 degrees Celsius, in other words, when it is in negatives, that substance is always ice. So ice can go below 0 degrees Celsius. And that process of ice will reach, when it reaches 0, it means that here we shall have that ice turn into liquid or turn into water. Then at this point, for it, we shall have water. Then at this stage here, that is when our water will always turn into vapor, water to vapor. And beyond that point, at this point, is where we have what we call vapor. So the process at this point here is what we call melting. So at that point, where our ice is turning into water, we call it the melting state. And at the melting state, there is always constant temperature. Whenever something is melting, it means that the temperature is constant. Whenever something is changing its state, it means that there will be constant temperature. Still, the same thing happens here when it comes to what we call vaporization. So at the vaporization stage, here we have water turning to vapor at a constant temperature. So still here, our temperature is still constant. Now, whenever you are given these scenarios, ask yourself, is it going to be a heating one or it's going to be a cooling one? So whenever it is a heating one, you'll find that your graph will look like this. So you'll have a change of temperature, and we know that water here will boil at around 100 degrees Celsius. So the moment it reaches 100, it means that now your water is going to turn into vapor. And at this point here, when we have a change of state from ice to water, is what we shall be calling the latent heat of fusion. And latent heat of fusion means that we have a change of state from ice to water at constant temperature. When we talk about vaporization, it means we have a change of state from water to vapor at constant temperature. So this is how a heating curve looks like. When it comes to a cooling one, for a cooling curve, we shall have something like this. We shall have our graph, we shall have it. It will start from up there to a given temperature. Then this one can be our 100 degrees Celsius. Then it comes down, then it changes, and then it go down. So here is where we have our vapor turning into water. Then here we have our water turning into ice. And then down here is where we shall have what? Our ice. Now, these curves are going to be very important when we are dealing with calculations involving the change of state, whereby a substance changes from one state to another. So let us start on our calculations, hoping we are together. Now here we have how much energy is needed to take 3.5 kilogram of ice at negative 25 degrees and turn it into liquid water. So here we have a change of state. We have a substance that is changing from ice into a liquid. So meaning that here, since our temperature is going to be increasing, you are noticing that we are starting with ice at negative 25 degrees Celsius, meaning that it keeps on increasing up to when the substance changes into the liquid. So if I am to apply our cooling curve at this stage, what am I going to have? It means that I am going to come here. I have like this. This is our heating curve. So we have our ice. This is the ice that is at negative 25. Negative 25. So it means that its temperature must first increase up to when it reaches what? 0 degrees Celsius. Remember, here we have our temperature and here we have our time. The moment it reaches 0, it is going to come and turn. So at this point, it means that our ice must turn into the water. And that is the stage you call the fusion stage. The fusion stage of the change of the state. After changing into that state, this water will continue to boil, and they have told us that they want us to boil this water up to when it reaches the 50 degrees Celsius. Now, this is how our curve is going to look like. We have a change of state. Here we have ice. Here we have ice to water. And at this stage here, we have what we call water. So we are going to let, when we are dealing with these calculations, let CW stand for what we call specific heat capacity of water. Always it is good practice to define what you are using. When CI is going to be specific capacity of our ice, and then we shall say M to stand for the mass of ice, maybe MI, then MW to stand for the mass of the water, and then we shall use theta to stand for our temperature. So those are some of the variables that we are going to use. Now, allow me to label that when we are changing at ice, here I'm going to call this quantity of heat Q1. Here, allow me to call it Q2. And then here, I call it Q3. So I'm going to find out at each level, how much heat do we need? That for us to change from ice to water, how much heat do we need? Then at the end of the day, we shall find out how much energy is needed to change a substance at 3.5 kilograms of ice at negative 25 to the 50 degrees. So allow me to divide here, and I send out the first one. We call it our Q1. And this is the energy to heat the ice from negative 25 degrees Celsius to 0 degrees Celsius. So I'll say now my quantity 1 is equal to the mass, because at that level we are still having ice. It will be mass of ice times specific capacity of ice times the temperature change. So here, when you look at our graph, you notice it very well that our graph here, we are going to have our change of state. This is negative 25, and this is where we have 0. So the mass of ice, it was given as 3.5 times specific capacity of ice, which is 2100, then times the temperature change. So our temperature is changing from negative 25 to 0. So negative 25 is your initial. Then this 0 is what we call our final. So we shall have final temperature minus the initial temperature. So here we shall end up with 3.5 times 2100, then times 25. Because when the negative and negative meets, we get a positive. So here when you multiply, use on your calculator, you get 183,750 joules. That is our quantity 1. Then we have our second one, we call it Q2, and that is now the energy to melt the ice at 0 degrees Celsius. So whenever you meet that flat line, that line where there is no change of temperature. Whenever there is no change of temperature, it means there we deal with latent heat. Whenever you have just the straight line, that means we are going to be dealing with latent heat. So what does it mean? It means here at this point, we are going to be dealing with latent heat of fusion. And latent heat of fusion means that you are changing from ice to water at 0 degrees Celsius. And how do we find the quantity of heat? Because we know that latent heat is hidden. So that one is obtained by having the mass of the ice that is turning into the liquid, then times latent heat of fusion. So our mass is 3.5, then times 336,000. So when we multiply, we have 117,600 joules. Then the last one is the Q3, whereby we want to find out the energy required to heat water from 0 degrees Celsius to the 50 degrees Celsius. So that quantity of heat we are calling Q3 is going to be our mass of the water, specific capacity of the water, then times the temperature change. What do you need to remember? Remember that now on our graph, we have from here where we have 0 degrees and this is where we have our 50. So we want to find out how much heat do we need such that our water can boil from 0 up to when it reaches the 50. So that means that our initial temperature at this point is 0 and our final temperature here is equal to 50. So in order for us to get the temperature change, we shall always have the final minus the initial temperature. So our Q3 will equal to the mass of the water. So the mass of the water is equal to the mass of the ice that has melted. So we shall have it as 3.5 times first capacity of water, which is 4,200, then times the temperature change, which is 50 minus 0. So here we shall have our 3.5 times 4,200, then times our 50. So when you multiply, you have 735,000 joules. Now, after finding the quantity of heat at each stage, it means that now we can find out the total energy required for the whole process. So I'm going to say now the total energy, it means we shall have Q1, I add it on Q2, I add it on Q3. So here we shall have 183,750 plus Q2, which is 117,600, then plus 735,000. So our total energy, heat energy, when you add, you have 209,470 joules. So that is our total energy required now for the whole process in order for our ice to turn from ice to liquid at 50 degrees Celsius. So that is how you can approach such a number. Okay, we can look at another number. And for the second number, we are going to try out the UNEP number that appeared last year for the candidates. And this question is telling us that your sister leaves home for work at 7:20 a.m. and as a must carries tea in a flask. One morning, she needed to prepare the tea she carries, but remembered that the only water she had in the house was 5 liters in a saucepan of 0.2 kilograms in a deep freezer. On removing the saucepan from the deep freezer, she realized that all the water turned into a block of ice. It was 7 a.m. and she was worried about leaving late, but decided to heat the saucepan containing the block of ice with her heater, rated 4.22 kilowatts, until all the ice turned into water and the water boiled ready for tea. Now they want us to determine how long it took your sister to boil the tea and explain whether your sister was able to leave home for work at 7:20. Now, when you look at this item, it involves us moving from a lower temperature to a higher temperature because you know that ice in order for us to be able to get water, ice must first turn from ice to water, and then there we can go on and boil our water to obtain our tea. And we know that in order for us to obtain our tea boils at 100 degrees Celsius. So it still involves the change of state from 0 to up to when we reach 100. So meaning that here it is a heating curve. You must heat something. So here we shall also apply the heating curve. But in real life, how do they look like? Whenever you put a substance in a freezer or in a fridge, in a deep freezer, it always turns into ice. So the picture you're seeing here, these are the blocks of ice that the lady found when she opened. And here she's now using the heater to heat such that now that water, that ice block can turn into the water. So now we are going to first demonstrate using our graph. How will it look like? Now, when you look at this question, always it is a good practice for you to summarize the different things you have. Now, when you look here, they're telling us on morning she needed to prepare the tea she carries, but remember that only water she had in the house was 5 liters. Now, here we need to find out water, quantity of water. Now, the quantity of water we have, quantity of water is equal to 5 liters. But we know that when we are making calculations, we always make them in scientific form, in their standard form. So meaning that the quantity of water is in liters, meaning we must convert those liters to find out in the 5 liters, what is the mass of what is its equivalent. Now, what do you need to know? Now, you need to remember that always 1 meter cubed is equivalent to 1,000 liters. Now, we have to convert the liters to kilograms, because for any calculation we are making, it must be in standard units. So what do you remember? You need to remember that density is always given by mass out of volume. So since we know the density of water, we have the volume of water, so we can find the mass of water. So the mass of water is going to be the density of water, then times the volume of the water. But like I've already told that 1 meter cubed is equivalent to 1,000 liters. So as my side work here, I will say 1 meter cubed is equivalent to 1,000 liters. Then I ask myself, when I have 5 liters, because you know that the 5 liters here, it is standing for what? For volume. So now I'll say, what about my 5 liters? So I say, what is equivalent to 5 liters? So when you cross multiply, you'll find that you have 5 out of 1,000, which is the same as 5 exponent negative 3, and these are meters cubed. So, but we know that density of water from here, density of water is 1,000. So we shall say that now the mass of water is equal to density, which is 1,000 times 5 exponent negative 3. So when you multiply there, you'll end up with 5 kilogram as your mass of water. So our mass of water is going to be 5 kilograms. So here we shall say where MW is what stands for our mass of water. Then when we continue, the mass of the saucepan, here we shall say mass of the saucepan, So that one, I want to call it MS is equal to 0.2 kilograms. On removing the saucepan from deep freezer, she realized that all the water turned into block of ice. It was 7 a.m. and she was worried about leaving late, but decided to heat the saucepan containing the block of ice with her heater rated 4.22 kilowatts, meaning that now they have given us our power, which we can call P, is equal to 4.22 kilowatts. But you know the standard units for power is watts. So, but you need to remember that 1 kilo is equivalent to 1,000. So in order for us to obtain our power, we shall say that our power is equal to 4.22 times 1,000, which will end us giving us 4 to 20 watts. So that is our power. Now, after understanding this, now it means that we have the mass of saucepan, we have the mass of the water, we have our power. So we need to know the different states that our ice is going to go through. So we are going to go back, and now I want to use the heat curve to show you how it looks like. Now, when I look at the heat curve, this is my curve where I have my temperature and I have here my time. So this one is in seconds, temperature is in degrees Celsius. So they told us that ice was initially at 0 degrees. So mean that this ice of ours is going to be at 0 degrees, 0 degrees. I don't know whether it will come out well. That is our ice at 0. Now, this ice, we have ice turning to water. So when it reaches here at a given, after applying a given quantity of heat, the temperature is going to increase up to when it reaches the boiling point, which is 100. So here it is the water that is turning. So what does it mean? The quantity of heat, the total quantity of heat needed for the process. We know that we must first turn the ice to water. And this process here is what we call the fusion. So this is what we call the latent heat of fusion. So where ice turns to water. Now, what do we need to do? Now we need to find out the quantity of heat the quantity of heat for the whole process. Now, in order for us to get, you are going to allow me to say here is going to be our, let me call it Q1, and here I'll call it Q2. So now I'm going to come and I start on my calculation to find out the energy required at each level, the energy that we shall require at each level during our calculations. So when you look at what we have, we are going to first find quantity 1. We are going to say the energy to melt our ice, to melt ice at 0 degrees Celsius. Now, in order for us to get that, we shall say that the quantity which we are calling 1 is equal to the mass of ice, then times the latent heat of fusion. Now, the latent heat of fusion, do we have it? Yes. So here, mass of ice is equal to 5, because when you look at our question here, we have said that the water, because it is the water that turns into the ice. So the mass of water and the mass of ice will be the same. So mass of water will equal to the mass of ice. So here we shall have 5 times the latent heat of fusion, which is 336,000. So you place your calculator, and then here we shall have 1680,000 joules. Do not forget the units. So that is the first one here that we have obtained. So the quantity of heat we have obtained is for this level here. That is the one. Then we go to the second part that we need. The second one is the energy required to heat our water from 0 to 50 to 100 degrees Celsius. Now we are going to say energy to heat the water from 0 degrees Celsius to 100 degrees Celsius. Now, in order for us to get that quantity of heat, here we note that our initial temperature is 0. Then the final temperature for us to get the water is 100. This is the final temperature here. So we shall say that the quantity of heat Q2 will equal to the mass of the water, specific capacity of the water, times the temperature change. So you can even label that T, this one stands for temperature change. So I'll have the mass of water, which is 5, times specific capacity, which is 4,200, times the temperature change, which is 100 minus 0. So here I'll have 5 times 4,200, then times 100. So when you place the calculator, you'll have 2100,000 joules. But remember, this water of ours, it was in a saucepan. What does it mean? You had your saucepan. This is our saucepan. And in the saucepan, you had your water. Here, this is the saucepan, and this is the water inside the saucepan. So meaning that as you are heating the water, the saucepan also gains heat. Here, remember you are applying heat. So when you heat, it means there are two things that gain heat. Saucepan is going to gain the heat. Saucepan gains heat, but also the water will also gain the heat. So what does it mean? Since the water is gaining and the saucepan is gaining, also we need to find out the energy required, the energy to heat the saucepan from 0 to our temperature of 100. So we shall say here, energy to heat the saucepan, because it is the saucepan that will feel the heat first. The saucepan from to heat the saucepan from 0 degrees to 100 degrees. So that one we shall call it Q3. Hoping people have understood that point. Because remember, when you are heating something, the saucepan itself is going to gain heat, and that heat will be transferred to the water. So that heat is taken in by the saucepan in order for it to be able to transfer it to the water. So here I will say the mass of the saucepan, specific capacity of the saucepan times the temperature change. So the mass of the saucepan, it was given as 0.2. Specific capacity was 900, then times the temperature change, which is going to be 100 from to minus 0. Because initially, remember, ice was put into the saucepan. So when ice was put into the saucepan, it means that it was really very, very cold. So they had the same temperature of 0 degrees Celsius. But when you apply heat, the saucepan starts also getting warm, like that. So when you place here, you shall have 0.2 times the 900, then times the 100. And this one will end up giving us 1800 joules. Now, those are the heat that has been gained in the process. So in order for us to find out the total quantity of heat for the whole process, for this ice to turn from 0 up to when it reaches the boiling point, I'm going to come and I say now the quantity of heat. So the total quantity of heat. So I say total quantity of heat gained will equal to Q1 plus our Q2 plus our Q3, which is equal to, now you add everything you have, the 1680, add it on 2100, add it on 18000. So when you add everything, you end up with 3798000 joules. Now, this is the quantity of heat. But you need to remember that what are we finding? We are finding the time. So in order for us to find the time, you know that the amount of heat that is being supplied by the heater, so I can say that heat supplied by the heater will always equal to the heat gained by the saucepan, gained by water, and heat gained by the saucepan. So what does it mean? It means that our quantity of heat here by the heater is always given by power times T times the time is equal to the quantity of heat. So here is our total heat, which we have obtained as 3798000. Then our power, according to you remember our power from here was 4220 that was being supplied by the heater. So here we shall have 4220, then times our time is equal to 3798000. Then here I will say T is equal to time. Okay, then in order for us to find, we shall divide by 4220, divide by 4220. So our time, when you press your calculator, you'll end up with 900 seconds. Now, it means that for the whole process, for the water, for the ice to be able to turn to water and boil up to 100, it will take about 900 seconds. But when you look at 900 seconds, they are not easy to understand. So you need to take them into things that people can understand well. So our time, being that is equal to 900 seconds, we know that in 1 minute, we have 60 seconds. So you ask yourself, how many minutes are in 900 seconds? So when you cross multiply, you'll find out that you'll have 900 divided by 60. And 900 divided by 60, you end up with 15 minutes. So we have 15 minutes. And therefore now I can say that it takes, you can say that it will take my sister approximately 15 minutes to boil the tea, and she will finish at 7:15 a.m. So that is how you can answer that part. Then when you look at part B wanted us to explain whether or not your sister was able to leave home for work at 7:20 a.m. Now, when you look at this question, since the time we have found is 7:15 a.m., that it means that here your response is going to be yes, my sister will be able to leave home for work at 7:20 a.m. Why? Because she has been in position to boil her tea before that time, and she was able to finish at 7:15, meaning that she still has additional 5 minutes in order for her to finish her other business. So that is how you can attempt such a number. So this is how you would have attempted such a number that came. Okay, so now you have some other numbers here that I want you to try out. So you'll try out that number and then to check whether you have understood. So we shall end here for now, and we shall continue from here when we meet again.